Hi everyone, it's Michael. So I know I haven't posted a video in a while, so I'm sorry about that. I've been a little busy, but I have a very fun problem for all of you today. So this problem is from the 1998 IMO Shortlist, and I believe it's problem 18. So nowadays they have all the problems separated into algebra, geometry, number theory, and combinatorics. But back then, I think they were all just combined into one single list, and this was number 18. So if you want to try to solve it, feel free to pause the video. Alright, so now I'm going to go over the solution. So we have a triangle ABC. D, E, and F are the feet of the altitudes. And the line through D parallel to EF meets AB and AC at R and Q. So AB you have to extend in this figure. The line EF meets the line BC at P. And we want to show that the circumcircle of PQR passes through the midpoint of BC, which I've called M. Okay. So basically we want to show that PRMQ is a cyclic quadrilateral. And the most natural way that I saw to do this is by power of a point. So if we can show that PD times DM is RD times DQ, that would get us there. So the trick is trying to figure out how do we utilize, or how do we find the product RD times DQ? Well, so one thing you can notice is that triangle AFE is similar to triangle ARQ because EF and QR are parallel from the problem statement. So, and you also might notice that, so I've labeled the orthocenter of the triangle H, and people who do a lot of competition geometry will notice that AFHE is cyclic because AFH is 90 degrees and AEH is 90 degrees. So if AFHE is cyclic, then if we took the midpoint, which, or not the midpoint, the intersection of the diagonals, which I haven't labeled, but if we call it K, for example, then FK times KE would kind of in a way resemble RD times DQ, but on a smaller triangle that's similar to it. So instead what I'm going to do is I'm going to take the triangle AFHE and I'm going to scale it up so that F maps onto R and E maps onto Q. And we can do that because triangle AFE is similar to triangle ARQ. And in that case, we want to see where H would go to. So H would go to a point G. And then the figure AFHE is similar to the figure ARGQ. So this is called a homothety, for those of you that know it. Basically, you're taking one figure, AFHE, and you're just scaling it up. You're scaling all 4 points, F, H. You're scaling F, H, and E all up to be at R, G, and Q, so that the new figure ARGQ is similar to AFHE. Okay, so how does this help us? Well, we knew AFHE is cyclic, so since we're just scaling it, ARGQ has to be cyclic, and that means that we can use power of a point to find RD times DQ, is in fact AD times DG. So I'm going to write this all up now. So here's the homothety at A. It takes all those points to what I mentioned, A to F, R to E, and a homothety at A, it takes F to R, E to Q, and H to G. And so since, like I mentioned, since AFHE is cyclic, ARGQ has to be cyclic. This is just the way of writing it out here. And so RD times DQ is AD times DG. But we wanted to show that RD times DQ is PD times DM. So by transitivity, we want to show that AD times DG is PD times DM if we want to solve the problem. So basically, we want to show that the quadrilateral APGM is cyclic, and that would get us there. So I'm kind of using power of a point forwards and backwards a bunch of times. Okay, so how do we show that APGM is cyclic? Well, one way is we can try to show that angle MAG is equal to angle MPG. And so that's the approach I'm going to take here. Now, one thing that can help us, if you've seen my video on the HM theorem, this comes into handy a lot of times. It's number 5, video number 5 on my channel. But basically it says that pH is perpendicular to AM. So that's not exactly the statement of the HM theorem, but if you watch that video and you see the proof that I give, that's exactly what I end up showing, that pH is perpendicular to AM. And in fact, there's another way to see this, even without the HM theorem. It uses a little projective geometry, so I'm just going to briefly touch it. But basically, quadrilateral BFEC is cyclic, and M is the center of that circle. And so therefore, due to the way the lines are arranged, pH has to be the polar of that circle through BFEC, the polar of it with respect to point A. So that means, again, that pH has to be perpendicular to AM. So I just very sort of quickly mentioned 2 ways of getting to this. So I know it wasn't a full, to see the full explanation of this way, you'd have to watch the video, and to fully explain the other way, you'd have to know a little bit about polars and projective geometry. So I'm not going to go into detail on that here, but anyways, pH is perpendicular to AM, and so that helps us compute angle MAG. So I'm going to do a little angle chase here. So MAG is the same as HAM. So basically angle HAM is 90 minus angle AMD. That's clear because AMD is 90 degrees. And 90 minus AMD, well, if pH is perpendicular to AM, then 90 minus AMD would be HPM. Okay. So if we want to show APGM is cyclic, then we want to show really that HPM is MPG. And that would actually mean, if that were actually true, that would mean that H would be the reflection of G over PC. So how do we show that? How do we show that HD is equal to DG? So I'm going to do another couple cyclic quadrilaterals and an angle chase. But basically, I'm going to end up showing that angle HCD is equal to angle GCD, and that would show us that HD equals DG, which would get us to where we want. Okay, so first, note that since GDC is GQC and they're both 90 degrees, we have to have GDQC as cyclic. And then also, since BFC is 90 degrees and BEC is 90 degrees, BFEC has to be cyclic. So both of them for the same reason. And these are going to come in handy for angle chase. So angle GCD has to equal angle GQD because this is cyclic. And then angle GQD has to equal angle BEF. Now, why is that? It's kind of by the homophily, because GQD has to equal angle HEF because AFHE is similar to ARGD, but HEF is BEF. So GQD has to equal BEF. But then because BFEC is cyclic, BEF has to equal angle BCF. So what have we shown here? We've shown that GCD is BCF. So basically we've shown that BC is the angle bisector of GCF. And so that means that HD has to equal DG. And that's because HG is perpendicular to BC. So now we're almost there. So we've shown that these two are equal. HD is equal to DG. And now we can sort of reverse engineer this to get us our proof that we wanted, that APGM is cyclic. Okay. So we have angle GPM is angle HPM, and that's because we just showed that since DG is DH and H is a reflection of G over point D, then we have to have GPM is HPM, and then HPM is equal to HAM using our argument using the HM theorem, and then angle HAM is sorry, it's covered up a little bit here, is equal to angle GAM, and so we have angle GPM is equal to angle GAM, and so APGM is cyclic. So whoops, I think I just by moving this, I think I just removed my next step. But so I'm going to actually just type it in for fun. But since APGM is cyclic, basically that essentially gets us to where we want, because that means, and I'm going to type it in here actually so you can have a little fun seeing exactly what it looks like. So that means that AD times DG is equal to PD times DM. And we know from earlier that AD times DG is RD times DQ. So this has to also equal RD times DQ. So there we go. And because of that, since PD times DM is RD times DQ, then that means that PRMQ has to be cyclic, and that solves the problem. So I'll just type that in here. All right, so I hope you all enjoyed this problem. If you like this video, feel free to give it a thumbs up. And if you want to see more like this, please subscribe to my channel. And if you have any other solutions too, I'd love to see them, because I know this one was kind of long, but I'm sure there's a shorter way to do it. So thanks everyone.